In this video, I'm going to talk about the stability of linear control systems. So in the previous videos, we talked about how to compute the solution for the linear time invariant system and linear time invariant system. So stability is sort of, you can consider stability as a property of the solution of the linear system. In particular, stability, you can consider this as the ability of a control system to remain in a bounded region with or without control input. So here I give you a very simple example which shows the stability of two different systems. For the first one, let's see if I put a blue ball over here. So this is like the shape of the surface we have. So as you could imagine that the ball will kind of go down and possibly go back and forth a couple of times and then settle down at the bottom of this point. So assuming that we have friction, of course. On the other side, so that's the shape we have. On the other side, if we have a different shape of structure, okay, it's kind of different from the previous one. So if I put the ball at this location, as you can imagine, even if I don't apply any force, so object, this ball will move to the left and down toward the trend, down toward the hill, basically, right? If this is the trend, it will continue, okay, go to infinity, for example, you can sort of see there's no stable point. It will keep going until reach to the infinity, if this go deep to infinity, okay? So the first case you sort of can see is stable because it doesn't matter where you started, as long as you stay within this region, for example, you don't go beyond it. Now, you sort of see if you put it over there, and it will, assuming we have friction, so it will stabilize at this point, okay? Even if I put it over here, this location, okay? Let me use a blue one. Even if I put it over here, you can sort of see it will still sort of go down it will still go down. If you put it over here, it will still go down. And assuming you have friction, so you could go back and forth a couple of times and settle down at this point. So this is the stable, it's called stable because it can remain in this region. Well, this one, I don't know, we don't know where this blue ball will go to, because it go to infinity, and it's not stabilized at any region. So you can sort of get a basic impression about what stability means for a control system. So in a more specific way, we're going to give this definition of what stability means, of course in different context, okay? So when we go to the mathematical formulation of the linear system, we typically given this ABCD form, as I mentioned before. So here this AT and BT, CT and DT, they may be time variant, they may not be constant. Of course, if they are constant, we are called a linear time invariant system. If they are varying, they're changing over time, so this is called linear time variant system, okay? So generally, if we consider linear time variant system, so if we define the phi t0 as a transition matrix, so you can check the previous video about solution to LTV about the definition of a transition matrix. So once we have the transition matrix, actually you can compute the solution y sub t as ct times phi t0 x0. So this is the transition matrix, and we have additional term. Okay, so you sort of can see the first term over here is only related to the initial condition x0. So it doesn't rely on the control input. So we also call this yzi is output with zero input, because I don't care, assuming that my input is 0, so this will be my output. The other portion will be just yzs, called output with 0 initial state. You assume the initial state is 0, so this is what you get by giving a certain input u sub t. Okay, that's the actual output of y sub t if x0 is 0. So the stability part actually talks about the two components individually. So for the output with 0 input, which means only consider this part, we talk about what we call internal stability. You can sort of intuitively think about that. You don't have the input. Input actually is called external, basically. So that's what we call internal stability. So we'll talk about the marginal stability and asymptotic stability, the two different stability properties. So the second component we're talking about, what is the impact of input on the output, which is called input-output stability. Okay, this one we don't consider x0, so this is considered to be 0. We only consider this part, okay? So which is called input-output stability. Okay, it's for both the internal stability and input-output stability. Of course, internal stability including two different stability properties. One is called marginal stability, one is asymptotic stability. So I'll talk about the definitions and the condition to guarantee those stability later on. The other one is called input-output stability. Okay, so this is more related to how the input will impact outputs, as mentioned before. Okay, so both internal stability and input-output stability will also talk about both for the linear time invariant system and linear time invariant system. Okay, apparently, as you can see, the linear time invariant system and linear time for linear time invariant system, it's a little bit easier because A and B and C and D, they are constant. Well, for LTV, linear time invariant system, because AT, BT, CT, and DT, they are time variant, so it can be challenging to verify their stability properties. Okay, now we start with this linear time invariant system. Okay, we'll talk about the stability property for linear time invariant system later on. Okay, so before talking about internal stability, we'll start first with the input-output stability. So it's the input-output stability, and also we're talking about the linear time invariant system only here. Okay, we don't talk about linear time invariant system. We'll talk about later on. All right, so for input-output stability for linear time invariant system, we have one stability property we call BIBO stability. Okay, which stands for bounded input and bounded output stability. So we pick the first letter, BIBO, so it's called BIBO stability. Okay, so again, it is assumed here, since we're talking about input-output stability, so we assume the initial state to be 0. Okay, so the BIBO stability is defined as this. So if we give a control input u sub t, whose norm is less than or equal to some constant value, which means my ut is bounded, and this um is less than infinity. Okay, this is bounded, and if this one implies that my y sub t, which is output, y sub t has also a finite norm, which means the norm will be less than equal to this ym. So this norm is what we define. So this will be the vector norm. So I mentioned in the mathematical background parts about the vector norm. So it can be any norm. It doesn't mean it's two norms, p norm, whatever norm. As long as norm is fine. Okay. So if a bounded input, which means a bounded norm of this input, implies a bounded output, in other words, a bounded norm of the output, then the linear system is called BIBO stable. Okay. Again, under the condition, the initial condition is 0. Okay. So that's the definition, of course. Then the next question is how to check if a control system is BIBO stable, right? So we know this is BIBO. The BIBO stable, you can sort of imagine, consider this way. If you give finite input, so means the finite input excites finite output. So that's what we can interpret what the BIBO stability means. So finite input excites finite outputs with a 0 initial condition. Okay. All right. So the next point is how do I check if a control system is BIBO stable? Okay. So the first one is you can use direct method. Okay, since I already know the relationship between the input and output, which is given, assume here is 0, so you don't have this part anymore. So this one BIBO means, which means if I bounded this input, I have bounded output. I just have to verify, okay, the whole thing is bounded if the norm of u sub t is bounded. Okay, if I can verify this, yeah, I can make sure the system is BIBO stable. Okay, this is the direct method. You can use the definition. Okay, the second method is called indirect method. Okay, indirect method is we don't check this. Okay, it sounds a little bit complicated. since we have to do a lot of things. First, we have to compute this transition matrix. We have to do the multiple the products. Okay, then we do the integration, and also we have to compute the dt time. This is pretty straightforward, I guess, but this is pretty complicated. Okay, so especially for certain cases, the transition matrix, this is very hard, very difficult to compute. It may be very difficult to compute. If you remember in my previous video, so we only talk about two cases that you can compute the transition matrix by hand. One is when you use the definition of transition matrix, when you can ignore all the high order integrals, that yeah, you can compute the transition matrix. The second one is you have a diagonal matrix. The AT is diagonal. Okay, then you can compute the transition matrix. Other than that, it can be very challenging to compute what is the transition matrix is. Okay, so that's why the integral method may be very important. Okay, in these cases. Okay, so for the integral method, we start with a little bit simple method, which we system which is called single input and single output system. Okay, we'll talk about a multi input and multi output system later on, but it's easier to see from the single input and single output system about some of the properties, and then we can generalize the condition to the multiple input and the multiple output system. Okay, so single input, as you can imagine, your input, you have one input, and also you have one output. So that's the single input and single output system. Okay, so a single input and single output system, which means if I want to make it a little bit specific over here, so your u sub t is dimension is 1, only a scalar, and also yt is a scalar. Okay, that's the single input and single output system. So a single input and single output system is BIBO stable if and only if the poles of the transfer function have negative real parts. Okay, so here the transfer function, okay, if you don't know transfer function, so I here put a video that I recorded earlier talking about how to compute the transfer function of a control system. Okay, what it basically says, the poles of the transfer function have negative, and I emphasize negative real parts. Okay, so it has negative. If it has 0 real parts, it's not okay. If a positive, it's not okay. It must have negative real parts. Okay. All right. So what is the transfer function? As mentioned, so you can check this video for more details if you don't know or don't remember that. The transfer function is to be very brief. So the transfer function is given by this is g sub s, notation wise written by g sub s, and it's given by y sub s divided by u sub s. Okay, so this is, you can say this is the Laplace transform of my y sub t. This is Laplace transform of my u sub t. So that is the u sub s. This is y sub s. Okay, and also when you set the initial condition to be 0, which is consistent with what we say over here, because the initial condition is 0. Okay, so if I do over here, so the transfer function is the Laplace transform of the output divided by the Laplace transform of the input when the initial condition is set to be 0. Okay. All right. So let me give an example showing that how do we use this one to verify how to use this condition. Okay, to verify if the system is BIBO stable or not. Okay. So here, give me example. Here is assume that I have a spring. Okay, one end is hanging like on the ceiling, for example, and the other side of this spring, you're hanging object which has a mass of m. Okay, so here assume the direction here, right here, is from the this is like from the north, the top, and this bottom over here, like from ceiling, then this is the floor, the bottom is the floor. So I define this direction as x, and also the 0 location of this x of this object is when this you don't apply anything over here. Okay, you don't apply anything over here. So which means this is one. Okay, this point is defined 0 when my spring, the force of spring is equal to 0. which means when at this point your spring does not give you any force, doesn't you push you, pull you, doesn't push you. So this is the when x0, so this spring does not have any force applied to the object. Okay, that's the initial zero state of x. Okay, so here assume that I apply some force, which is u sub t over here, to this object. Okay, this is my input. Okay, and also I assume that the constant for the springs, for the force applied to the object associated with a different length, okay, for the spring is given by negative k of x. Okay, which means if you go longer polar direction, you get a negative force, because the force you will drag, you will pull this object up. If you push it, which means you have negative x, so you will pull it, so your force will pull you down. So the actual force applied to object to this object by the spring is given by negative kx, okay, negative xt. Sorry. The force is just u sub t. Okay. So if I use the Newton's second law, I know the acceleration, the m time acceleration, this is acceleration, is equal to the force applied to the object. The force includes m of g, this is gravitational constant. So this is force created by the gravitational field. And this u sub t is the actual input we apply. And minus k of axt, this is the force created by the spring. So this is total force applied to the object. So according to the Newton's law, we have m times a is equal to the total force. Okay. Apparently, so y sub t is x sub t is the actual location of this object. Okay, at different time. Okay. So I want to see you this one. So this is a single input and single output. This is single input, single output system, because the input is just one. I have force, which is u sub t, and the output is just my location. Okay, so this is y sub t. So it's a single input and single output system. All right, so let's do some analysis using this condition to verify is BIBO stable or not. Okay, so there's one hidden assumption here. Is I assume that my spring can move arbitrarily long, or maybe go to negative, going negative direction, whatever we can say it. It can go positive direction or negative direction. Okay, infinite length, which may not be true in practice, but here the model just said I don't have a limit on what xt would go from negative side, both negative and positive side. Okay, just be careful. Okay. All right, so here let's define for this one, because it's not a standard ABCD form, right? It's not an ABCD form like the standard state space representation. So I want to write this in the ABCD form. Okay, so let's do something. Okay, let's define x, the blue x, as this is a vector, which is x, the black x and the black x dot. So black x is the location, position, and black x dot is the velocity. Okay, and in other words, you can sort of view as I have the blue one has two vector, is a vector, so I have two entries. One is x1, one is x2. x1 is the black x, and x2 is the x dot, black x dot. Okay, once you define this variable state, so what do we have is x1 dot is x2, okay, I mean the blue one, and x2 dot is x double dot, as you can see, right? Because x2 is x dot, black x dot, and you take one more derivative is just the double dot of the black x. So double dot of the black x can be obtained from here. So the equation we just got from the Newton's second law. Okay, we just have to divide both sides by m. So then this left hand side becomes x double dot t. Okay, so we divide the right hand side by m. So I have mg plus ut minus k xt. Okay. Then we simplify a little bit. So we have we have the x2 dot t, the blue x2 dot is mg plus ut divided by m minus k over m times xt. So here xt is the blue x1. Okay, so I just replace it by blue x1. And this one we do some change, because mg plus ut, I just represent this by a blue u sub t. Okay, as I mentioned over here. So this make it a little bit simple. Okay. Also, this one does not change the BIBO. Because a bounded use of t, the blue use of t means also bounded use of t, right? So it doesn't matter. I don't have to check the stability BIBs for the black use of t. I can consider the blue use of t because it doesn't really matter. A bounded use of t, blue use of t, it also means a bounded black use of t. So that's equivalent. So in other words, the original system is BIBO stable. This one, the red one here, if and only if the blue one over here is BIBO stable. Of course, my y is also x1. Okay. The nice thing for the blue one is I can write this in Statespace representation, the standard form we typically use. Okay. So to summarize, by putting the x1, x2 together as the new state, okay, whose derivative is given by, derived by the two equations, of course. We put them together as a matrix in a matrix form. So I have 0, 1, negative k over m, 0, times x1, x2. This is what when you put this equation, these two equations, this guy and this guy in this form. Okay, you have this. Okay, so 0, 1, negative k over m, 0, x1, x2, plus 0, 1 over m use of t. Okay, that's equivalent to these two equations. These two equations I want to write over here. That's equivalent to that two equation. Okay. Of course, my y will be x1, which is y is 0, 1 times x1, x2. Okay. Of course, here you can sort of see I have another one, which is d times use of t, and here d is 0. You just consider d is 0. Okay, basically. Okay, let's use also the red one. This d and d is 0. Okay, I don't have d. Now here I have a single input and single output system. Okay, the transfer function is computed when we assume this x0 is 0. Okay, x0 is 0. Okay, so the computer transfer function, because I want to know the transfer function is what? The transfer function is defined as y sub s divided by u sub s. So I need to look at this Laplace transform. I don't use this is in the time domain. Okay, I need to look at it in the S domain. So what do we do? Yeah, we can take a original. Let's take a look at the general form for linear time, because this is a linear time invariant system, right? So let's take a look at general form. Okay, what is it's a general LTI system. Let's see what is the transfer function. Okay, then we can just plug in those A, B, C, D value to get the actual transfer function for this system. Okay, what do we have over here? Okay, if you look at the general LTI system, we have x dot t is axt plus but, and yt is cxt plus dut. So it's a, b, c, d are constant. So this a, b, c, and d, they are constant. Okay, so because I want to look at the transfer function, so yeah, I have to apply Laplace transform for both equations. So I do Laplace transform both for the top one and for the bottom one. And then I define this Laplace transform of xt is xs, capital X, big XS. Laplace transform of yt is big y sub s. Laplace transform of ut is big u sub s. Now we use the property. This one you can use. You can check the table about the derivatives. Okay, derivatives is just s times this Laplace transform minus the initial condition. Okay, which equal to the right hand side is pretty straightforward because the linear property of the Laplace transform means you can pose a outside. Okay, right before that, then you can a times L of xt, because the L of xt is just xs, so it's a times xs, and you can put b outside. B times L ut is just bus. So similarly, you can apply the Laplace transform to the second equation over here, which means ys is cxs plus dus. Okay, now we can drop the initial condition over here because the initial condition is set to be 0. So the first equation, we can further write this as xs is si minus a inverse times b times u sub s. Because you can pull this one to the left hand side and merge this xs together as si minus a times xs. And then you multiply both sides by xi minus a times inverse on the left hand side, of course. So there's an intermediate step that I dropped over here from here to here, which is this guy. If I move this one to the left hand side, okay, so I have si minus a times xs is b u sub s. Okay, so if I multiply both sides by si minus a inverse here, and also left multiply here, so this will cancel out to get me solution XS. Then I get this solution, okay? So once I have this XS, I just have plug in the XS over here, right, to the solution of Y sub S. So I have Y sub S, C XS, replace XS by what we have found over here. So it's C SMS A inverse B, and also I can combine, because this U sub S combined together is plus D times UF, U sub S. So this is my the relation between the U sub and the Y sub S when the initial condition is 0. Okay, so we can start from here. We sort of can see, yeah, my Y sub S over U sub S is just given by this part, right? If we pull this one to left hand side, it's YS divided by U sub S is just given by this. So which is C SMS A inverse B plus D. That's the transfer function for general linear time invariant system using the state space representation. Okay, since we already know this A, B, C, D, we have A and B and C and D over here, so we just have to plug in those numbers. Okay, so C is 1 0. Okay, we just plug in 1 0, and SI minus 0 1. So this is A. Okay, this is B, right? D is 0, so you can just ignore. D is 0, so you ignore the D. So I don't want to go to the detail about the computational inverse of all the matrix operations, but when you compute the solution of the transfer function, it becomes 1 over ms squared plus k. Okay, so this is my transfer function. Okay, so if you look at this one, the condition for the BIBO stability is to check the poles of the transfer function to make sure the poles have negative real parts. So what are the poles? The poles are when you set the denominator of your transfer function to be 0. Okay, the denominator of the transfer function, so this is my denominator, you set it to be 0. That's how you compute the pole. Of course, the mass cannot be negative, and the k is also non-negative for the spring. Okay, so k and m, they're all positive, so we can find a solution to this guy. Okay, if you set it to be 0, you have s squared is negative k over m, right? So this guy is negative k over m is less than 0. Okay, so when you take a square root of that, you actually get two solutions. One is S1 is square root of k over m times I, so this I is the square root of negative 1. Okay, S2 is negative square root of k over m times I. Okay, so we just have to check the real part. So this is the imaginary part. As you can imagine, the real part is plus 0. You can see this is plus 0, right? Because this is the real part. The real part of S1, S2, they are 0. Okay, they're not negative. Okay, because the condition says the poles have negative real parts, right? So because of when we compute the real parts of the pole, they are 0. It's not negative. So because the poles just have 0 real parts, which is not negative real parts, so the system is not a BIBO stable. Okay, you sort of see a little bit confusing why this system is not a BIBO stable. It looks like you cannot put down all the way down, right? You cannot put all the way down. You put it, it looks like it's gonna stop. But what happens is the input may not be in that way. For example, what I do is I just pull it. Let's say I pull it to what happens. I'm going to show you what's going to happen. Why it's not a BIBO stable. Let's say I'm going to apply a constant value u sub t at the very beginning. Okay, pull it. Okay, then the object apply and then release it. So this ball will go down, right? Go down and then go up. Because it should go back, right? Go back and then go back again, right? It should go there because I assume there's no friction. Unless you assume the friction, that's different. No friction, so it should come down at this point again. Okay, your little object is going. The little object should go up and down, up and down, up and down, right? Once it go up and down, even after applied, I don't apply constant force. I just apply a force at the very beginning. It will do that, as you can imagine. So once I do that, this object, once it reaches the second time, for example, reaches this point, I apply another force over here. So it's sort of going down more and more. So then at this point, I should give another force. Okay, you basically what you do is you apply force, instantaneous force, and you release it, and then you let it do oscillation behavior, and then you at the extreme point of the oscillation behavior. At this point, you apply a force to pull it. You just need to apply a bounded force. You don't have to apply infinite force to get a larger oscillation. more oscillation. So you can keep doing that until you get more and more oscillation. So that's why it could oscillate to infinity, basically. That's why it's not a BIBO stable, because even if I only apply bounded input, but the output can go infinity. So that's what it means by BIBO stable. So this is counterintuitive, because in practice this spring cannot go infinitely long, right? In either bottom or go up, it cannot do that. In practice, this wouldn't happen, but this is an example just showing you that if that would be the case, you can allow this spring to go infinitely long, either both up and down. Then yes, this can go infinity. Okay, in practice, this is not a BIBO stable. Okay, this is BIBO stable because in practice, you have a limit. You cannot go too far away for the spring from the 0 point. Okay, so that's the single input and single output system. Now let's see how this one kind of condition can be generalized to multi-input and multi-output system. Okay, so for the multi-input and multi-output system, we still have the standard. This is still for linear time invariant system. I want to emphasize, not linear time invariant system. So I still have the standard ABCD form as in the state space representation. The difference here is the U sub t and Y sub t, they may have multiple components. They don't necessarily have just one component. So for this type of system, linear time, multi-input and multi-output system, it is a BIBO stable if all eigenvalues of A have negative real parts. That's one condition we can say, okay? So pay attention to here, the statement over here. So this one only says if, which means, yeah, it's not required. But if all eigenvalues have negative real parts, it's guaranteed it's BIBO stable. However, if some eigenvalues are negative, some eigenvalues are positive, we don't know. You cannot say it's not a BIBO stable. Also, you cannot say it's BIBO stable. So this is just a sufficient condition. The other one is the linear time invariant system. This is a necessary and sufficient condition. The linear time invariant system for the multi-input and multi-output system is BIBO stable if and only if the pose of each element of the transfer function, which is defined as this. So this is the same as I give it in the right over here. This is the transfer function. Okay. So only if each element of the transfer function just have negative real parts. So because we have multiple input and multi-output system, so G sub s typically it's not just one number. It could have multiple components. Each one so each of this entry, for example, is something like this. Is something like what we compute over here. So each one is ns divided by ds, is numerator divided by some denominator. You have to check for every component or every element of this guy must have negative real part. The pose of this each component have negative real part. So that's the condition for the BIBO stable for the multi-input and the multi-output system. So as this is pretty straightforward, because if it's only for one of this, you have to check the pose for this individual components. If you have a multiple one, you have to check each one. This is quite straightforward to understand. So here I won't talk about details about an example like this. This is a very specific example, but I want to give you a general example. If I give you the transfer function of the system, you can verify it's BIBO stable or not. For example, if I give you the transfer function G sub s for the multi-input and multi-output system given by this, assume I have two entries, two elements basically. So this is my first element, this is my second element. Okay? So first element s minus 1 times s plus 2 divided by s minus 1 times s plus 2 times s plus 3 times s plus 4. And the second element of my transfer function is s minus 1 times s minus 6 divided by s minus 1 plus s plus 2, s plus 3, s plus 4. So this guy is divided. I have to check each element, right? Because this one, notice that this is a cancel out, right? This is cancelled out. This is cancelled out. So they're not poles, okay? They're cancelled out. You don't consider as poles. So your poles actually you set this to be 0. You use s plus 3, s plus 4. You set it to be 0. Yeah, you have two poles. One is negative 3 and one negative 4. Yeah, they have negative real parts. Similar for this guy, we have three poles, right? Basically, we have s plus 2, s plus 3 and s plus 4, you set to be 0. Again, because this is a cancel out, you don't consider that as a pole. So I have s is -2, I have 3 poles, -2, -3, and -4. So yeah, for each element, the poles of each element have negative real parts. That's true. That's true. So it is BIBO stable. Okay. If I give you another example, the differences here is, yeah, this is pretty much the same as previous one. The only difference is this also cancels out. The first entry element will be the same. The second element will be, I don't have s minus 1 over here. So if I check the pole, yeah, for the first one, the pole for the first element will be the same. You still set s plus 3 times s plus 4. So check the denominator to be 0. Okay, again, because this cancel out. Okay, so I have -3, -4, they're poles. They do have negative real parts. Let's check. For the second one, so I don't have anything that can cancel out any entry, any component in my denominator. So I still have 4 components. So I have if I set denominator to be 0, which is s minus 1, and s plus 2, s plus 3, and s plus 4. So I set it to be 0. So I have 4 solutions or 4 poles. So 1, -2, -3, and -4. Yeah, this is not right because I have one of these poles have positive real parts, so which is not okay. So this is not a BIBO stable. Okay, so that's what I hope this will be clear to understand the basic concept of the BIBO stable and the condition to guarantee the BIBO stable for the linear time invariant system.